All right, so our objective today is to understand the closure property with various subgroups of real numbers. Now you may say, individually, I may understand those words. Together, I have no idea. So our goal is by the end, you will understand. Does that make sense? Okay, so I'll write the objective at the top here. To understand, so OBJ, to understand the closure property with various subgroups of real numbers. So let me ask you this. The word subgroups may be the one that's a little bit strange. Can somebody name some subgroups of real numbers? Okay. Spencer, give me one.
Natural numbers.
We've got natural numbers. Okay, so I'm going to write this down. Natural numbers. Okay, and Maddie?
Percentages.
We got, you know what, we're going to keep that under just generic rational. Most of the times when I'm looking at how people categorize, they take some of the groups and they just say, you know what, they're not that special, we'll just throw them in the generic, they're rational. Okay, which, by the way, I just gave away one, right, didn't I? And so you also gave me integers. Okay, what are other subgroups of real numbers? Gregory?
Whole numbers.
We got whole numbers. Okay, I think there's at least another, there's a huge one that nobody has mentioned yet. Patrick? Fractions is, again, we're going to kind of couch them underneath rational. So I'm going to do a little subgroup here. So it's a sub of a sub. And we don't usually break it down. So fractions would be in here. Percents would be in here. What else would be in there? Do you think that's a kind of the general? Molly? Decimals are going to be in there too. Okay. All right. We still are missing something kind of vitally important. Kia? Kai. Sorry. Thank you. He's a big group there that we kind of do need to include. Irrational numbers. And I think those are the major subgroups. Okay? All right. So are you ready for your definition of closure? It's kind of interesting. Can I move on? Are we good? Yeah? Okay. All right. So closure property. Oops. Let me go back to black. And it's more of a idea than it is quantifiable. Like we could do commutative property 2 plus 3 is going to give me the same answer as 3 plus 2. We don't quite get to write it that way. So it's a little bit more abstract. So it's a set is closed. So that's how we talk about closure property. If something is closed under an operation, if whenever the operation and remember we do have 4 of them. We have adding, we have subtracting, we have multiplying, and we have dividing. Is performed within the set the answer, I'm going to put a comma, the answer is also a member of the set. Now we're going to break this down because I know that probably your ears are even glazed over. Okay. So, just keep this in mind. Whenever you're talked about closure, you need two things. You must be given a set of numbers and it could be very specific. It could be the numbers 1, 0, and -1. It could be very general, all real numbers. Okay, so the set can be very small or infinite, depending upon the situation. The other thing you're going to be given is an operation, so adding, subtracting, multiplying, and dividing, to be performed upon the set of numbers. Okay? I'm going to give you something to think about that a lot of kids forget. An operation may be performed between a number and itself. Okay? All right, so let's break down what this means by doing an example. So we're going to pick a particular set of numbers. I'm going to pick the largest set I could think of, and then I'm going to pick the smallest set I can think of, okay? And we're going to look at it from adding, subtracting, multiplying, and dividing's perspective. Does that make sense? Okay. So the largest set that I can think of that we know would be which set? Real numbers. So that's all the rationals, which includes fractions, decimals, integers, whole numbers, natural numbers, percents, all of that, square roots of perfect squares, numbers squared, all of that fall into rational, and the irrationals, the non-repeating, non-terminating decimals. Okay, so we've got every single number that you have studied. We get that as our choice. Okay, so let's look at it for addition. Okay, and the question is, if I add two real numbers, is the answer a real number? So one of the major things that you're not looking for is you're not looking for what supports this. Say, yeah, 1 plus 1 is 2. Oh, 2 is a whole number. Whole number is rational. Rational is part of real. Yes! What you're looking for is this guy. Look for a counterexample. And a counterexample is an event, a situation in which when you added two real numbers, the answer was not a real number. So what is our option if it's not real? What did I tell you was our other option if it wasn't real? Remember, Spencer? It's imaginary. Now, for all intents and purposes, the only thing that we could possibly get if this was not closed would be, can we get an imaginary number? Because that would be the only thing that's outside the set of real numbers. And an imaginary number looks like this. So think through every possibility of adding numbers together. is it possible to get a negative under the square root sign? Okay. So even if we did, let's say, radical 2 minus radical 5, would I get radical negative 3 for that? No, because the math is being done with these radicals. I don't do stuff inside. So that's not going to equal negative 3. So there is no value we could come up with in the real number system that when I add two real numbers, I get something that's not real. So what we say is that addition is closed for real numbers. All real numbers will add to give me real numbers. Okay? All right, let's try subtraction. Can we come up with a counterexample where when I subtract two numbers, I get the square root of a negative number? Anyone? Any ideas? Can you come up with one? I'm hearing nothing. So we have, let's do it this way. We can say it this way: real numbers are closed for subtraction. So there's different ways to actually make this statement. Okay, we needed always in our statement, though, we need to include what group we're talking about. We need to say if it's closed or not closed, and then we need to say what operation. So those three pieces will always be there. Okay, what about multiplication? For real numbers. Oh, not read numbers, real numbers. Can I possibly multiply any two numbers and get two real numbers and get an imaginary number? Is that possible? Yes, no, otherwise? Is there any way to multiply and get radical negative 3? Or, excuse me, radical negative 3? The answer is no, it's not possible. So we've got closure again. We can say, again, here's our other way. Multiplication is closed for real numbers. Okay. And what do you think it's going to be for division? Yeah, pretty much. So the reality is, when you have large groups of numbers, generally speaking, there's no counterexamples. We can always find an answer that's in that same group. So what we're going to do flip side is now give you a very small group. It's a very famous small group. You'll see this example a lot. So we'll say real numbers. So I'm just alternating ways of saying it. Are closed for division. All right, so let's talk about a very specific group. What if my set of numbers included -1, 0, and +1? So that's all that I have in my group, those 3 numbers. So we're going to look at closure for those 3 numbers only, okay? So let's look at addition first. And what I'm looking for is that counterexample. Is there any way that I can add the elements, the members of that group, in such a way that I get an answer that's not in the group? And most people go, let's see, -1 plus 0 equals -1. Well, that's in the group, so that's good. How about -1 plus 1 equals 0? Well, 0's in my group, so that's good. And then we can do 0 plus 1 equals 1, and that's in my group. And kids, stop there. But what are you forgetting? Remember, I gave you a big warning at the beginning. Ian?
You can multiply and you can add numbers by themselves.
So if I add 1 and -1 and -1, what do I get? I get -2. Is that a member of the group? So immediately I stop and I say closed, or not closed, sorry. For addition. And the reason why it's not closed is because my answer was outside that group. So if I drew a picture of it, here's my -1, here's my 0, here's my 1, and sitting by himself banished is -2. Okay, so he was outside the group means it's not closed. All right, let's try subtraction. Now that you kind of get the hang of it, can you come up, is there a counterexample where when you do subtraction, you get an answer that's not in the group? You think of one, Brian?
Yeah.
What do you get?
-1 minus 1 equals -2.
Oh, man. Look at that. Right there. Not working. And that's all we need is one counterexample, and we're done. So, not closed for subtraction. Here's -2 out there again, right? Poor guy, makes your heart sad. How about multiplication? Can we come up with a counterexample there? Is there any way I can take 2 of those numbers, multiply them together, and the answer is not in that group? Ian? You don't think so? All right, let's play it out. So we've got -1 times 0 equals 0. That's in the group. -1 times 1 equals -1. That's in the group. Oh, we got bamboozled by this one with addition. How about -1 times itself? That equals 1. Oh, that's in the group. Well, how about 0 times 1? That's 0. That's in the group. All right. How about 1 times -1? That's -1. That's in the group. How about 1 times 0? That's in there. Now, you could say, why would you even test that, Ms. Rosner? We got the community property multiplication. That was kind of a waste of time. And I'd say, smart people, you're right. So we don't have to test in our operations that we know are commutative, the commutative ones. Okay, we already know it inherently. We got one more to try. How about 1 times 1 equals 1? That's in there. So guess what? No, I didn't say 2. Did I say 2? He said 2. Okay. It's your secret shame. Patrick said 1 times 1 is 2. Okay, it's not so secret anymore. No. We make those mistakes all the time.
No, I was just saying.
Yeah. So what we have here is it is closed for multiplication. So that's exciting. All right, so we got one more to do. Let's try. Division. Now, without trying it, prediction, yes or no? Closed or not closed? Okay, so we think closed. Can anyone think of a counterexample where the answer you get from the dividing process is not in that group? All right, then let's test them. Let's see, we've got -1 divided by 0 is,
Oh.
dang it. It's undefined. Remember, we can't divide by 0. That's asking us to take -1 and put it into no group. So guess what? My very first attempt, keeping the pattern that I've been using, out the window. And that's the only one that blows it, is that one right there. Okay, so it's not closed for division. We thought it would be, but it's not. Okay?